All right, how's it going, you guys? Another LeetCode video today. This one's called Course Schedule 2. So there are a total of num courses we can take, labeled from 0 to num courses minus 1. We're also given an array prerequisites, where prerequisites I is going to be equal to AI BI, where we have to take BI first before we can take AI. So basically the second element in a pair of prerequisites is going to be the prerequisite. It'll be the second element. Second element's the prerequisite of the first element. Return the ordering of courses you should take to finish all of the courses. If there are many valid answers, return any of them. If it is impossible to finish all the courses, return empty array. Okay, so there's a couple things to talk about here. So if it's impossible to finish all of the courses, or if there's a cycle in the graph of directed edges, of courses and their prerequisites, then they just want an empty array, okay? They don't want any ordering if it's impossible, right? Kind of understandable, right? Because, how would you even derive the order if there's a cycle? That makes sense. But it's a little bit, a little confusing because it's like, okay, do we do like a DFS sort of approach like we did with course schedule 1? I mean, you can do that, but I think it's a little more confusing. For this problem, I think the easiest way to solve it is just with a topological sort. So that's more of a breadth for search than it is a depth for search. We're going to be solving this with a topological sort. So let's not beat around the bush. Let's just get to this algorithm demonstration. So that's how we're going to be coming up with the order, is with a topological sort. So the first thing we need to do is construct the graph. All right, so let's build this graph. There needs to be, each course, right, has an integer value, and each course is going to have its own node. So let's build this graph. So we have a 0, a 1, num courses is going to be 6. So there's going to be six nodes. Okay. And then there's going to be some edges, right? And the direction of our edges is going to correspond to the, the way the courses can be completed chronologically. So basically, for example, 0 is a prerequisite for 1. So the direction of that edge is going to be from 0 to 1. You would take course 0 first, and then you would take course 1, etc., etc. So 0 is also a prerequisite for 2. So let's put that arrow in. We're just going to go over these one at a time. This is the same way we will be constructing it in the code. So 1 is a prerequisite of 3. 1's a prerequisite of 3. 3 is a prerequisite of 5. So let's add in that edge. Let's see, 2 is a prerequisite of 3. And 5 is going to be a prerequisite of 4. So as we can see, just with this example, we can already tell there's no cycles. But there's going to be, a way we can check that when we're done with our topological sort. So let's do our topological sort. So basically what we're going to need is a frequency map of the number of in-degrees at each node, right? So if you're not familiar with what in-degrees are just an in-degree is an edge that is incoming to a node, right? So a directed edge that's entering a node is an in-degree. So like this 3 would have how many in-degrees? It would have 2 in-degrees because there's 2 edges, directed edges entering this node, right? So let's just count up all of the in-degrees. I'll mark those with red. And we're going to be doing this in code with like a hash map. So this 3 has 2 in-degrees, 5 has 1, 4 has 1. This 0 has 0, 1 has 1, 2 has 1, And yeah, that's pretty much it. So we've counted the in degrees for every node. So basically we're gonna have a queue. So let's get a queue going over here. And we're basically going to add every node that has 0 in degrees to our queue, right? So right now there's only one node, there's 0. So we'll put that at the front of our queue. Okay, because it's got 0 in degrees. And then basically what we do is we take every neighbor of 0 and we're going to decrease those indices by 1. Okay, and if any of those indices become equal to 0, then we're gonna put the indice, or the node rather, back into the queue. So whenever a node has 0 in degrees, we're gonna put it into the queue. Okay, so 0 is already in the queue, right? We're looking at its neighbors, 1, okay, and 2. We're gonna subtract, we're gonna take away an in degree, right? We're just gonna subtract 1. Okay, so now these are both gonna have 0 in degrees, right? Okay, and since they both have 0 in degrees, they can go into our queue. Okay, so let's, and just to, we're only iterating over what was in there previously, right? All of these, the neighbors for this guy, right? So, or just the, the top value. So now we're gonna add the 1, and we're gonna add the 2. Okay, and then we're done with the 0 now, so we can remove it from the queue, but we're gonna put it into our result, right? So we're gonna have a result down here. So 0 is gonna be the first course in that chronological order. Okay, so now we're done with the 0. Okay, so we're gonna look at 1's neighbors now. We're at the top of the queue again. Looking at this 1. Okay, so we're gonna look at 1's neighbors. It's got one neighbor here, which is this 3. Okay, so we're gonna subtract a in degree from it. So this 2 is gonna go down to 1. All right, but it's not 0, so we're not gonna be putting it into our queue. All right, okay, so let's go to 2's neighbors. But we are done with this 1, so we need to get that out of the way, right? We're popping the 1 from the queue because we already did its neighbors, and then we got to add it to our, whenever we're done with a number at the top of the queue like that, we add it to our order whenever it's got 0 in degrees. Okay, so now we're done with this 1. We didn't have to add anything to the queue. We're at this 2. Okay, we look at its neighbors. It's got one neighbor, which is the same node here. We're gonna knock off an in degree. So now the in degrees are 0. So now we can put it into the queue. So, and I'll put it up here because we're about to get rid of this 2. So we put it into the queue. Our 2 is gonna go away, right? It's gonna go into our chronological order here. Let's get it out of the queue. Okay, so now we're gonna go through 3's neighbors. So 3 has one neighbor, it's the 5. We would take off an in degree, and so let's go ahead and just do that. We see that there's 0, so it is going to go into the queue. All right, and then we're done with the 3. Okay, all right, so now we're dealing with the 5. We see that it's got, this 4, it's got one neighbor. We would knock off an in degree. Since it has 0 in degrees, we can put it into the queue. So now we're done with the 5, right? It's gonna go into a result. And then finally, we would, deal with the 4. The 4 would also, we would knock off its in degree when we add it, or before we add it, right? So the in degree of this 4 would also be 0, and then we, would add it to the result. So yeah, so this is going to be the ordering, and that's what we return. Now you might be, wondering, okay, but what if there's a cycle The easy way to detect that is basically if there's any cycles, we're not going to be able to decrease all of these in degrees to 0 with that algorithm. Like it's just not going to work. One of these in degrees would still be 0 or still have some larger than 0 value, at least one of them, right? So then we would know, okay, there's a cycle. And what does that mean? Well, we can only add courses to our result if, and we can only add them to the queue if they have 0 in degrees, right? And that's the only way they can get into results. So basically the size of result is going to be smaller than the number of courses. So if this is smaller than this, then we know there's a cycle. Alternatively, you could check through the frequency map after topological sort and see if there's a non-zero in degree at any node. That's another way. Then it see, okay, this one has 1 in degree still. Then you see there's, must have been a cycle. So that's how you check that. There's a couple ways you can do that. But yeah, in terms of the time and space for this problem, it's just going to be, so the time is just going to be big O of V plus E, because that's just how topological sort is going to work. We have to visit every vertex and every edge at least once. And then for the space complexity, in terms of the space complexity, we're going to have a couple of data structures, right? We're going to have a queue, which could potentially have, as many vertices as there are, courses. We're also going to have a frequency map and a graph. The graph itself, the space of the graph requires, big O of V plus E. So it's also just going to be big O of number of vertices plus number of edges for the space also, mostly just for the graph. That's going to be the dominant data structure there for space. So yeah, let's get into the code for this problem. So the first thing we want to do is construct the graph, right? So we'll just use a hash table. We'll have the integer as the key will be the prerequisite, and then we're going to have a vector of integers for all of those neighbors. We'll just call it graph. Okay, then we just have to iterate through every prerequisite. So say P, short for prerequisite. So for P and requisites, we're going to, and let's just do this on one line, we're going to insert the prerequisite, which is the second value, right? So P1, and then we push back its, its neighbor, which is the next course, right? Which is the first value or the first element in that, in that vector of 2 elements, right? So yeah, so now we've constructed the graph. Okay, so we've got to count up in degrees now. So we're gonna need like a frequency map, right? So let's just create another hash map, right? And use the same data structure to count in degrees, but it'll just be int, right? The int will be the course or the the node, and then the value will be the number of in degrees, right? So we'll just call this in degrees. Okay, so to find the in degrees, we just need to loop through the graph, right? So we're going to say for auto, and it's going to be a key value in graph. Oops, I had a pop up there. Okay, so for auto key value in graph, and then we're counting in degrees, right? So how do we do that? Well, we've got to go to basically just increase the in degrees for every neighbor, right? Because we know that in order to get to that neighbor, it must have had an in degree. So anyways, yeah, we're just going to say for, nested for loop for auto neighbor in kv.second, right? That's like the list of neighbors. We're just going to increment all of those in degrees for the neighbors. So we'll say in degrees at neighbor plus plus, and that's going to count all of our n degrees. Okay, one thing I'm noticing though, we've also got to know when there's an n degree of 0, right? And this isn't initialized, these aren't going to be initialized to 0 by default. So we're going to have to set all of those to 0, right? So to do that, let's just iterate through num courses, right? And we can assume every course has 0 n degrees to begin with. So let's say for auto, or actually let's do a C style for loop. So for I equals 0, I is less than num courses, I plus plus, and then we can just set all of those n degrees, initialize them to be 0 to begin with. So we'll say n degrees I equals 0. Okay, and that'll handle that little discrepancy. Okay, so at this point we have the number of n degrees in a hash map. Okay, we also are going to need a queue. So let's create that queue. So we'll just make a queue of integers. Okay, and then we need to basically, I'll just call it queue. We need to put all of the nodes that have 0 n degrees into that queue. So let's iterate through our n degrees. So for auto key value in n degrees, okay, and then we're just gonna check, and let's do this on multiple lines. So if kv.second, right, that's the n degrees count. If that's equal to 0, then we can go ahead and push kv.first into the queue. So we'll say q.push, that's going to be kv.first, right, for that course. Okay, so we've got all of the courses with 0 n degrees into a queue now. So now we can iterate, we can do finally get into our topological sort. So while queue is not empty, so while there's still elements in there, we want to take the top course, right? So this is the course that has 0 n degrees. That was, that's up next, right? So we'll say int course, we'll just say is q.front. Then we can say q.pop, right, to remove it from the queue. And then we can, we're going to add, or we're going to decrement all of the n degrees of each of its neighbors by 1. So we need a for loop to do so. So we'll say for auto, and we'll just call it neighbor in graph course. So we're just getting all of the neighbors of that course. We're going to decrement the n degrees of each of those neighbors. So we're going to say n degrees on n degrees on neighbor minus minus, right? And then we also need to check if n degrees neighbor is 0, right? Whenever there's a node has reached 0 n degrees, we want to put it into the queue. So we're going to say q.push neighbor, essentially, just to get that into the queue when it's got 0 n degrees. And we can repeat the process for all of its neighbors to continue the topological sort. So that's pretty much it there. Remember, we also have a, at this point, whenever we're done with a node, it's had 0 n degrees, we went through all of its neighbors, then we can put it into our result, which we haven't made a data structure for yet. So we need a vector of integers, I'll just call it result, and we're going to just push this course to the result, right? And we can just push back. So we say res.push push back on, let's see, on course, right? Just adding that to the front of the result, or the back of the result rather, appending it to the end. So after that, we just need to check if we, successfully added each one of those courses to our result. Remember, because if any of those integers are greater than 0, then there was a cycle, and they want, in that case, remember, they just want an empty array. They don't want any solution, right? So, so we're gonna say, or we can just do Turner, or actually, yeah, let's say, so we're going to return if res.size equals num courses, right? That's what we're looking for. We can just return, if res.size is equal to num courses, this is what we're looking for. We're just going to return res, otherwise, I'm realizing this isn't really going to work. We kind of want an if statement here, so, and it's just going to get too long for a ternary. So anyways, yeah, so if res.size does not equal, or no, equals num courses, right, then we're just returning res. Okay, otherwise, there was a cycle. So we've got to basically just return an empty array. So we can just clear res and then return res. There's probably a cleaner way to do that. I might fix it up after the video. But anyways, yeah, in a nutshell, this is how you do this problem. Let's go ahead and submit it just to make sure I didn't write any bugs. Yeah, so hopefully this video helped you understand Course Schedule 2 better. If it did, leave a like and subscribe, and I'll see you guys in the next video. Peace.